Hello and welcome. Tonight we're taking a long, gentle journey into the cosmos to meet a paradox that feels almost impossible. How are the universe's most violent events unfolding in complete silence? Not quiet in the way a room goes quiet, but silent in the strangest way. Storms that can outshine galaxies, collisions that ripple space itself, forces so extreme they rewrite what power even means, all without a single sound. Before we begin, make yourself comfortable. Let your shoulders drop. Unclench your jaw. Now take a slow, deep breath in. Hold it for a moment. And exhale gently. Feel your body soften as if the day is loosening its grip. If you enjoy calm, story-led science like this, consider subscribing. It helps these nightly journeys find their way to more curious minds. All right, with the lights low and the pace unhurried, let's step into the silence and discover what the universe is doing when it seems perfectly still. You might think it sounds contradictory at first. After all, when we imagine violence, we imagine noise. Thunder cracking across the sky, explosions rattling windows, the roar of engines, the crash of waves against rocks. Violence and sound seem inseparable in our everyday experience. But out there, beyond our atmosphere, beyond the thin envelope of air we call home, the universe has been staging the most spectacular, powerful events imaginable. Stars exploding with more energy than our sun will produce in its entire lifetime. Black holes colliding and shaking the very fabric of reality. Magnetic fields so intense they could erase every hard drive on Earth from the distance of the moon. And all of it happens in absolute, complete silence. We'll discover why that is. We'll learn how scientists detect these cosmic giants without ever hearing a sound. And we'll visit some of the most extraordinary phenomena nature has ever created. Exploding stars, colliding black holes, objects so dense that a teaspoon of their material would weigh as much as a mountain. Magnetic fields powerful enough to warp the behavior of empty space itself. But we'll take our time with all of this. There's no rush. The universe has been doing these things for billions of years, and these stories deserve to be told slowly, carefully, the way starlight reaches us across the dark, patient and steady. So let the day fade. Let your breathing slow. And let's begin where all good cosmic stories begin, with silence itself. To understand why the universe is silent, we need to remember something simple about sound. Something so fundamental we usually don't think about it. Sound needs something to travel through. When you clap your hands together, you're not actually creating sound in that moment. What you're creating is a wave, a disturbance. Your hands compress the air between them, and that compression ripples outward in all directions, molecule bumping into molecule, like a whisper passed through a crowd at a concert. When those ripples reach your ear, tiny bones inside vibrate, nerves fire, and your brain interprets all of that as sound. Sound is movement, really. It's a dance of particles passing energy from one to the next, and then to the next, and the next. Here on Earth, we're surrounded by this dance constantly. Air molecules are everywhere around us, packed together just tightly enough to carry vibrations beautifully. There are about 25 quintillion molecules in every breath you take. That's 25 followed by 18 zeros. They're bouncing around, colliding, ready to carry any vibration that comes along. Water works even better as a medium for sound, actually. It's denser, so vibrations travel faster and farther. That's why whales can sing across entire ocean basins, their songs traveling thousands of kilometers through the deep. But space is profoundly different. Space isn't completely empty. That's a common misconception. Between the stars, scattered across the vast dark, there are atoms, mostly hydrogen, with a bit of helium mixed in, the simplest elements left over from the early universe. But these atoms are spread so incredibly, almost incomprehensibly thin. In the space between stars and what we call the interstellar medium, there might be 1 atom per cubic centimeter, sometimes less. To put that in perspective, the air you're breathing right now has about 25 quintillion molecules in a similar volume. The difference is staggering. If you could somehow hold out your hand in the void between stars, only a few atoms might drift through your palm each second. There's no medium to speak of, no crowd to pass the whisper through, no dancers to continue the dance. So when a star explodes, when it tears itself apart with more energy than our sun will produce in its entire 10 billion year lifetime, releasing as much light in a few weeks as an entire galaxy of hundreds of billions of stars, there's no boom, no thunderous roar, no crack that echoes across space. The shock wave races outward, slamming into whatever thin gas surrounds the star, heating it to millions of degrees, lighting it up like a cosmic firework. But beyond that immediate neighborhood, beyond that local bubble of disturbed gas, the explosion expands into silence. This isn't a flaw in the universe. It's not something missing or broken. It's just physics, quiet and absolute, following the rules that govern everything. But here's the beautiful part, the part that makes astronomy possible. Just because we can't hear these events doesn't mean we can't detect them. The universe speaks to us. It just uses different languages. Light, for instance. Light doesn't need a medium at all. It's perfectly happy traveling through the vacuum. It's made of photons, massless particles that zip along at exactly 299,792,458 meters per second. Nothing in the universe travels faster, and photons carry news of distant catastrophes across billions of light years, across billions of years of time, eventually reaching Earth where we can catch them and read their stories. When astronomers point their telescopes at the sky, they're not listening, they're watching. They're reading light the way you might read a book, analyzing which colors are present, how bright they are, how they change over time. Each variation tells them something about the source, temperature, composition, velocity, distance. Different wavelengths tell different stories, too. Visible light is what our eyes evolved to see, but it's just a tiny slice of the electromagnetic spectrum, less than 1% of all the light that exists. There's infrared light, which reveals heat, showing us warm dust clouds where stars are being born, or the afterglow of the Big Bang itself, cooled by cosmic expansion into microwaves. There's ultraviolet light, which shows us energetic processes, hot young stars, gas heated by shock waves, the active cores of galaxies. X-rays and gamma rays come only from the most extreme violence. Gas heated to tens of millions of degrees as it spirals into a black hole, the surface of a neutron star crushed to unimaginable densities, the annihilation of matter and antimatter, and radio waves, long and slow, can cross entire galaxies without being absorbed, carrying information about magnetic fields, about cold gas clouds, about the structure of the universe on the largest scales. Each wavelength is a different messenger carrying different news, and we've built instruments to detect them all. Then there are particles, actual bits of matter traveling through space at incredible speeds. Neutrinos, for example. These are strange little things, ghostly and nearly massless. They barely interact with normal matter at all. Trillions of them are passing through your body right now, most of them born in the nuclear furnace at the core of our sun, and they're going right through you without the slightest effect. Through the entire Earth, actually, as if it weren't even there. But when a supernova explodes, when a massive star's core collapses in less than a second, it releases a flood of neutrinos so vast, so overwhelming, that even though they're nearly impossible to catch, we can detect them. We've built huge underground tanks of ultra-pure water, shielded from cosmic rays by kilometers of rock, and we wait. When a neutrino occasionally, rarely, interacts with a water molecule, it produces a faint flash of light, and we catch it. In 1987, when a star exploded in a nearby dwarf galaxy called the Large Magellanic Cloud, only about 160,000 light-years away, detectors on Earth caught about 24 neutrinos from the explosion. Just 24 out of the trillions upon trillions that were released. But those 24 neutrinos told us something remarkable. They arrived several hours before we saw the light from the supernova. That's because the neutrinos escaped from the core immediately, while the light had to work its way out through the collapsing outer layers of the star. The neutrinos gave us our first glimpse into what happens at the very center of a dying star, confirming decades of theoretical predictions. Cosmic rays are different messengers. These are high-energy protons and atomic nuclei, some of them accelerated to within a tiny fraction of the speed of light. They arrive at Earth constantly, invisible rain from distant catastrophes, and they've been doing this for as long as Earth has existed. When they hit our atmosphere, they create showers of secondary particles. Some of those particles reach the ground. Some of them pass through you right now as you listen to this. Most cosmic rays come from supernova remnants, we think, accelerated by the shock waves of exploding stars. But the most energetic ones, the ones moving at 99.999% the speed of light, probably come from even more violent sources. Active galactic nuclei, perhaps, where supermassive black holes feed. We're still working that out. And then there are gravitational waves. These might be the most remarkable messengers of all, because they're so fundamentally different from anything else. When something truly massive accelerates, and I mean really accelerates, not just moving fast, but changing its motion quickly, it doesn't just disturb the matter around it. It sends ripples through the very fabric of space-time itself. Think about a stone dropped into a still pond. Ripples spread outward in circles, waves on the water's surface. Gravitational waves are similar, except instead of ripples on water, they're ripples in space-time. The actual geometry of the universe, the stage on which everything happens, gets stretched and squeezed as the wave passes by. For most of human history, this was pure theory. Einstein predicted gravitational waves in 1916 as a consequence of his general theory of relativity. But he thought we'd never be able to detect them. They're incredibly weak. Even the most violent events in the universe produce gravitational waves that barely disturb space-time. By the time a gravitational wave from two colliding black holes reaches Earth, after traveling across hundreds of millions or billions of light years, it stretches and squeezes space by less than 1/10,000th the width of a proton. Building a detector sensitive enough to measure that took decades of work. Generations of scientists and engineers developing new technologies, new materials, new techniques. The detectors that finally succeeded are called LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two of them in the United States, one in Louisiana and one in Washington State, separated by about 3,000 kilometers. Each one is an L-shaped tunnel, 4 kilometers long on each side, with mirrors at the ends. A laser beam is split and sent down both arms. The beams bounce back and forth between the mirrors hundreds of times, then recombine. Normally they cancel each other out perfectly. But when a gravitational wave passes through, it stretches space in one direction and squeezes it in the other. One arm of the L becomes slightly longer, the other slightly shorter. The laser beams get out of sync, and the detector catches it. On September 14, 2015, both LIGO detectors picked up a signal. A gravitational wave, a ripple in space-time, passing through Earth. The signal was brief, lasting less than a second, rising in frequency like a chirp. But encoded in that chirp was an extraordinary story. Two black holes, each about 30 times the mass of our Sun, had been orbiting each other for perhaps millions or billions of years. Slowly, very slowly, they spiraled closer together, losing energy to gravitational waves. As they got closer, they moved faster, orbiting each other more and more rapidly. In the final moments before they merged, they were circling each other hundreds of times per second, moving at a significant fraction of the speed of light. The gravitational waves they produced got stronger and stronger, higher and higher in frequency. Then they collided. They merged into a single, larger black hole, and for a brief moment, a fraction of a second, the collision released more power in gravitational waves than all the stars in the observable universe combined were releasing in light. More power than 100 billion trillion suns, and we felt it. Here on Earth, 1.3 billion light-years away, we felt space-time itself shake as those black holes merged. It was one of the most important scientific discoveries in the last 100 years. It opened a completely new way of observing the universe. Now we can detect events that produce no light at all, events that would otherwise be completely invisible. Since that first detection, we've found dozens more. Black hole mergers of different masses, different spins, neutron star mergers. Events we couldn't have imagined before, and we're just getting started. New detectors are being built, more sensitive ones. Detectors in space eventually that will be able to hear gravitational waves from supermassive black hole mergers in the early universe. We're learning to hear the universe shake. So that's our toolkit. Light across the entire electromagnetic spectrum, neutrinos from the hearts of stars, cosmic rays accelerated to incredible energies, gravitational waves from colliding black holes, silent messengers from a silent cosmos. And with these tools, these different ways of listening and watching, we've discovered just how violent the universe really is. We've mapped out the life cycles of stars. We've watched black holes grow. We've seen galaxies collide and merge. We've traced the creation of every element in the periodic table back to cosmic violence. Let's drift deeper now into these discoveries. Let's meet the stars that die, the remnants they leave behind, and the extraordinary violence that shapes the universe. Stars are, by their nature, gentle things for most of their lives. Our sun, for instance, has been shining steadily for about 4.6 billion years. Every second it converts about 600 million tons of hydrogen into helium through nuclear fusion. This releases an enormous amount of energy, which slowly works its way from the core to the surface, and then radiates out into space as light and heat. That energy, that outward pressure from fusion, is what holds the sun up against its own gravity. Gravity is always trying to crush the sun into a smaller, denser ball, but fusion pushes outward, resisting the crush. The two forces balance perfectly. This is called hydrostatic equilibrium, and it's the natural state of a star. Our sun will stay in this balance for another 5 billion years or so, quiet, steady, reliable, slowly, converting hydrogen to helium, releasing energy, shining. But for stars much more massive than our sun, stars born with perhaps 10 or 20 or 50 or even 100 times the sun's mass, this peaceful existence is much, much shorter. The bigger the star, the faster it burns through its fuel. This seems counterintuitive at first. You'd think a star with more fuel would last longer, but it doesn't work that way. More massive stars have stronger gravity, which means their cores are hotter and denser, and fusion happens much faster. A star 50 times the mass of the sun might live only 3 or 4 million years. Some of the most massive stars ever observed might live less than 1 million years. In cosmic terms, that's the blink of an eye. These massive stars burn through hydrogen quickly. When the hydrogen in the core runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. When the helium runs out, the core contracts again, and if the star is massive enough, it starts fusing carbon, then neon, then oxygen, then silicon. Each stage happens faster than the last. A massive star might spend 1 million years burning hydrogen, 100,000 years burning helium, a few hundred years burning carbon, and only about 1 day burning silicon into iron. The star's interior becomes layered like an onion, an iron core in the center surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen, each layer fusing into the next. Until it reaches iron, iron is special. Fundamental, really, to understanding what happens next. When you fuse lighter elements together, hydrogen into helium, helium into carbon, carbon into oxygen, you get energy out. That's how stars shine. That's what fusion is, converting mass into energy following Einstein's famous equation, E equals mc. But iron sits right at the peak of the binding energy curve. It's the most stable nucleus. Fusing iron into heavier elements doesn't release energy. It requires energy. So when a massive star's core turns to iron, something fundamental changes. The fusion stops. There's suddenly nothing holding gravity back. What happens next is almost impossibly fast. The iron core, which might have a mass of about 1.5 times the sun and a size similar to Earth, collapses. It doesn't collapse slowly. It doesn't take minutes or hours or days. It takes about 1 second, maybe less. The collapse happens at about 70,000 kilometers per second. roughly a quarter the speed of light. In less than a heartbeat, a core the size of Earth compresses into something the size of a city, maybe 20 kilometers across. The density becomes unimaginable. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos. The entire core becomes a single giant atomic nucleus, made almost entirely of neutrons packed so tightly that a teaspoon of the material would weigh about 1 billion tons. The collapse finally stops when the neutrons themselves can't be compressed any further. It's called neutron degeneracy pressure, a quantum mechanical effect that provides one last resistance against gravity. The core rebounds, it bounces, and a shock wave tears outward through the star's outer layers. This shock wave, combined with the pressure from the flood of neutrinos escaping the core, blows the star apart. The star explodes. We call this a core collapse supernova, or sometimes a type 2 supernova. The word supernova sounds almost gentle, doesn't it? Almost pretty, like a star blossoming into something new, something super. But the reality is staggering beyond normal comprehension. In a few seconds, a core collapse supernova releases as much energy as our sun will produce over its entire 10 billion year lifetime. If you could somehow harness all the sunlight that's ever hit Earth since the planet formed, and all the sunlight that will hit Earth until the sun dies, it would equal the energy released by a single supernova in about 1 second. Most of that energy, about 99%, is carried away by neutrinos, but the remaining 1%, released as light and kinetic energy of the explosion, is still enough to outshine an entire galaxy for weeks. From Earth, if we're lucky enough to be looking in the right direction, if the supernova happens in our galaxy or a nearby one, we see a new point of light appear in the sky where no star was visible before. Over days and weeks, it brightens dramatically. At its peak, a supernova can be as bright as 5 billion suns. Ancient astronomers called these guest stars or new stars because they appeared where nothing had been before. They didn't understand what they were seeing, but they recorded them carefully. In 1006 CE, a supernova appeared in the constellation Lupus that was bright enough to cast shadows at night. People could read by its light. It was visible in the daytime for weeks. In 1054 CE, Chinese and Arab astronomers recorded another brilliant new star in Taurus. It was visible in daylight for 23 days and remained visible at night for almost 2 years. Today, we can see the remnant of that explosion, the Crab Nebula, a beautiful, intricate cloud of glowing gas still expanding outward nearly 1,000 years later. In 1572, Tycho Brahe observed a supernova in Cassiopeia. It challenged the prevailing belief that the heavens were perfect and unchanging. And in 1604, Johannes Kepler observed the most recent supernova visible to the naked eye in our galaxy. We haven't seen one since, though statistically we're overdue. The star is gone now, but what it leaves behind is extraordinary. The explosion hurls the star's outer layers into space at thousands of kilometers per second. 10,000, 15,000, sometimes 20,000 kilometers per second. A few percent of the speed of light. All those elements that were forged in the star's core over millions of years, and in the explosion itself, are scattered into space. Carbon and nitrogen and oxygen, neon and magnesium and silicon, iron and nickel and cobalt. This is where these elements come from. Not all of them, but many of them. Every atom of calcium in your bones was created inside a star. Every atom of iron in your blood, the iron that carries oxygen through your body, was forged in a stellar core and scattered by a supernova explosion. You are quite literally made of material that was inside a star billions of years ago. Carl Sagan said it beautifully. We are made of star stuff. And he wasn't being poetic or metaphorical. He was being precisely, literally accurate. The explosion creates what we call a supernova remnant. The expanding shell of debris crashes into the surrounding interstellar gas, heating it to millions of degrees, lighting it up in X-rays and visible light. For thousands of years, a supernova remnant shines and expands, creating beautiful, intricate structures, filaments and wisps of glowing gas, showing where the shock wave has compressed and heated the surrounding medium. Eventually, after tens of thousands of years, the remnant fades and disperses, mixing with the general interstellar medium, enriching it with heavy elements. And those heavy elements become part of the next generation of stars and planets, and eventually people. But in the very center, where the core collapsed, something remains. Sometimes it's a neutron star. We'll talk about those in detail in just a bit. And sometimes, if the core was massive enough, if it had more than about 3 times the sun's mass, not even neutron degeneracy pressure can stop the collapse. The core keeps falling inward, past any point of return, past any possibility of support, and it becomes a black hole. Supernova aren't the only way massive stars die, though. Sometimes they die even more violently. For the most extreme cases, for stars that are incredibly massive or rotating rapidly or have exceptionally strong magnetic fields, we need a different word. We call these hypernovae. A hypernova is essentially a supernova on steroids. The basic process is the same. A massive star's core collapses, rebounds, and explodes. But the energy involved is 10 times greater, sometimes 50 or even 100 times greater than a typical supernova. These events are rare, exceptionally rare. We might see one in a given galaxy every few 100,000 years. What makes them different? Sometimes it's rotation. If a massive star is spinning very rapidly when its core collapses, the conservation of angular momentum means the core spins faster and faster as it shrinks. This can channel the explosion's energy in unusual ways, creating 2 narrow jets of material that burst out from the poles at nearly the speed of light. These jets plow through the star's outer layers and break free into space, carrying enormous amounts of energy with them. Sometimes it's the magnetic field. If the collapsing core has an extremely strong magnetic field, orders of magnitude stronger than normal, the field can be twisted and amplified during the collapse. This can drive an even more energetic explosion. And sometimes the star is just so massive, so energetic, that the explosion is off the scale of normal supernova. The result is an event that, for a brief time, can outshine hundreds of billions of stars. A single dying star producing more light than an entire galaxy. Let that settle for a moment. One star, brighter than a galaxy. Then there are pair instability supernova. These are different, stranger, more exotic. In the very early universe, before many generations of stars had lived and died, the gas clouds that formed stars were made almost entirely of hydrogen and helium. essentially no heavy elements at all. From these primordial clouds, the first stars could grow incredibly massive, much more massive than any star we see forming today. Perhaps 100 times the mass of the Sun, perhaps 200, maybe even more. In the core of such a star, temperatures and pressures become so extreme that gamma-ray photons, packets of pure light energy, become energetic enough to spontaneously split into particle-antiparticle pairs. An electron and a positron, matter and antimatter, appearing from a photon. This process, called pair production, steals energy from the core. The pressure drops suddenly. Gravity wins. The core starts to collapse. But in these massive stars, when the collapse begins, the temperatures get so high that explosive nuclear fusion begins throughout much of the star simultaneously. The entire star detonates. Not just the outer layers, but everything, the whole star. There's no remnant left behind. No neutron star in the center. No black hole. Just an expanding cloud of debris and energy. We've never directly witnessed a pair instability supernova. The stars that produce them existed billions of years ago in the early universe, before telescopes existed. But we've found indirect evidence in the chemistry of very old metal-poor stars, and computer simulations show us what these explosions must have looked like. They would have been spectacular, brighter even than hypernovae, and they would have enriched the early universe with the first heavy elements, making future generations of stars possible. There's one more type of supernova worth mentioning, different from all the others because it doesn't involve a massive star at all. Some white dwarfs, the dense remnants left behind when stars like our Sun die, exist in binary systems. Two stars orbiting each other, one of them a white dwarf, the other still alive. If the geometry is right, the white dwarf can slowly pull material off its companion. Gas spirals down onto the white dwarf's surface, adding to its mass bit by bit, year by year, millennium by millennium. White dwarfs are supported by electron degeneracy pressure, another quantum mechanical effect. But there's a limit to how much mass electron degeneracy can support, discovered by Subramanian Chandrasekhar in the 1930s. The limit is about 1.4 times the mass of the Sun. If a white dwarf accretes enough material to reach this Chandrasekhar limit, something catastrophic happens. The carbon and oxygen that make up the white dwarf ignite all at once in a runaway nuclear fusion reaction. The entire star detonates in what we call a Type Ia supernova. These explosions are remarkably consistent. Because they always happen at the same mass, they always release approximately the same amount of energy. They always brighten and fade in the same pattern with the same characteristic light curve. This consistency makes them incredibly useful. Astronomers use Type Ia supernova as standard candles to measure distances across the universe. In the 1990s, by observing distant Type Ia supernova, two teams of astronomers discovered that the expansion of the universe is accelerating, driven by something we now call dark energy. It's one of the most important cosmological discoveries ever made, and it earned the researchers the Nobel Prize in Physics in 2011. It's beautiful in a way. Even in death, these stars help us understand the universe. But let's return now to the remnants, to the objects left behind when massive stars explode. Because the violence doesn't stop with the explosion. Sometimes it's only just beginning. When a massive star's core collapses into a neutron star, what you're left with is one of the strangest objects in the universe. Imagine taking the mass of our sun, all 2 times 10 kilograms of it, something with a diameter of about 1.4 million kilometers, and compressing it into a sphere about 20 kilometers across, about the size of a city. Manhattan would fit on its surface with room to spare. That's a neutron star. The numbers are so extreme, they feel almost meaningless. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you could somehow bring a teaspoonful back, it would punch straight through the planet. Gravity at the surface is about 100 billion times stronger than Earth's. The escape velocity, the speed you'd need to leave the surface, is about 100,000 kilometers per second. That's 1/3 the speed of light. If you could somehow stand on a neutron star, which you absolutely couldn't, you'd be crushed by gravity into a layer less than an atom thick. Every atom in your body would be squeezed so hard that the electrons would be forced into the protons, forming more neutrons. These objects are the densest things in the universe that aren't black holes. Inside a neutron star, matter exists in states we can barely understand and certainly can't reproduce in laboratories on Earth. The surface might have a thin atmosphere of hydrogen or helium, only about 1 centimeter thick. Below that is a solid crust made of atomic nuclei and free electrons, squeezed into bizarre crystalline structures. Deeper down, the pressure becomes so intense that atomic nuclei merge into strange shapes, long rods, flat sheets, structures physicists whimsically call nuclear pasta because they resemble spaghetti or lasagna. And in the core, at the very center, the density might be so extreme that neutrons themselves break down into their constituent quarks, forming what we call quark matter. We're not entirely sure. The physics at these densities is poorly understood. We extrapolate from what we know, but we can't test it. What we do know is that neutron stars are violent in ways that have nothing to do with explosions. First, there's the rotation. When a massive star collapses, it spins faster. This is conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. But the degree of speed-up is extraordinary. A star that was rotating once every few weeks or months, which is typical for massive stars, suddenly collapses from a size of millions of kilometers to a size of 20 kilometers. The rotation speeds up proportionally. A newly formed neutron star might rotate hundreds of times per second. The fastest pulsar we've observed spins 716 times per second. That's faster than a kitchen blender, faster than a jet engine. A 20-kilometer ball of ultra-dense matter spinning so fast that points on its equator are moving at about 20% the speed of light. The centrifugal force should rip it apart, but gravity holds it together. As it spins, the neutron star drags space-time itself around with it in a phenomenon called frame dragging. Space near a spinning neutron star isn't static. It's being pulled around by the star's rotation, like honey being stirred. And because neutron stars have incredibly powerful magnetic fields, this rotation turns them into cosmic lighthouses. Neutron stars typically have magnetic fields about 1 trillion times stronger than Earth's. The field is generated by the motion of charged particles in the star's interior and crust. This magnetic field channels radiation into two narrow beams that shoot out from the magnetic poles. As the star spins, these beams sweep across space, like lighthouse beams sweeping across the ocean. If Earth happens to lie in the path of one of those beams, we see a pulse of radio waves, or X-rays, or visible light, depending on the pulsar. The pulses come with incredible regularity, precisely timed by the star's rotation. We call these objects pulsars, pulsating stars, though they're not actually pulsating. They're spinning. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who was then a graduate student at the University of Cambridge. She was analyzing data from a radio telescope designed to study quasars when she noticed something strange, a signal that repeated every 1.33 seconds like clockwork. At first, the team was baffled. The signal was so regular, so precise, that they half-jokingly considered the possibility that it might be a signal from an extraterrestrial civilization. They even gave it the nickname LGM-1, for Little Green Men 1. But it wasn't aliens. It was a neutron star spinning and beaming radio waves in our direction. Bell Burnell's discovery opened up an entirely new field of astronomy. Today, we've cataloged thousands of pulsars. Some pulse in radio waves, some in X-rays, some in visible light. Some pulse hundreds of times per second. Others pulse only once every few seconds. The most famous is probably the Crab pulsar, sitting at the heart of the Crab Nebula. It was created in the supernova of 1054 CE, and it's still spinning 30 times per second, almost 1,000 years later. Over time, pulsars gradually slow down. They lose energy through their magnetic fields, through the radiation they emit, through the creation of particle winds. The rotation slows. Millions or billions of years later, they fade into invisibility, still spinning, but too faint for us to detect. Quiet neutron stars drifting through the galaxy. Unless something disturbs them, unless they accrete material from a companion star, which can spin them back up, or unless they're born with something even more extreme, unless they're born as magnetars. A magnetar is a neutron star with a magnetic field so powerful it defies intuition, so powerful it warps the behavior of matter and space itself. Let's put the numbers in perspective. Earth has a magnetic field. It's what makes compasses work, what creates the auroras at the poles, what shields us from harmful solar radiation. It's gentle and protective, with a strength of about half a Gauss at the surface. A refrigerator magnet is about 100 times stronger, 100 Gauss. An MRI machine, one of the strongest magnets we routinely use in everyday life, has a field of about 10,000 to 30,000 Gauss. The strongest continuous magnetic field ever created in a laboratory is about 450,000 Gauss, achieved for brief moments in specialized facilities. A typical neutron star has a magnetic field of about 1 trillion Gauss. That's 1,000 billion. That's already incomprehensibly strong. And a magnetar has a magnetic field that's 1,000 times stronger than that. We're talking about fields of 100 million Gauss, 1 quadrillion Gauss, sometimes higher. At this strength, the magnetic field doesn't just attract iron. It doesn't just align atoms. It warps the quantum behavior of empty space. The vacuum itself becomes polarized. Light passing through it bends and splits in strange ways. Atoms are stretched into thin cigar shapes. Chemistry as we know it can't happen. If a magnetar existed at the distance of the moon, its magnetic field would be strong enough to erase every credit card on Earth, wipe every hard drive, destroy every magnetic storage device. From halfway to the moon, it would be lethal to humans, pulling the iron from our blood. But magnetars are dangerous in more direct ways too. Their magnetic fields are so intense that they stress the neutron star's crust. Imagine the crust of the star, already under unimaginable pressure from gravity, being twisted and strained by magnetic forces. The field lines thread through the crust, anchored to it, and as the interior of the star adjusts, the crust is put under tremendous stress. Eventually, something gives. The crust cracks. We call this a starquake. In an instant, the surface of the neutron star shifts by perhaps a millimeter, a tiny distance by human standards. But remember, this is an object where a teaspoon of matter weighs about 1 billion tons. The densities involved are staggering. A millimeter shift in the crust releases more energy than our sun produces in many years. The starquake generates waves that ripple through the star's interior and explode outward as bursts of X-rays and gamma rays. On December 27, 2004, astronomers detected one such burst from a magnetar called SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy. For 1/10 of a second, this object released more energy than the sun produces in 150,000 years. The burst of gamma rays hit Earth's atmosphere with such intensity that it ionized the upper atmosphere, disrupting radio communications. Satellites were temporarily blinded. The effect was measurable, even though the magnetar was halfway across the galaxy. If that same burst had occurred just 10 light-years away instead of 50,000, it might have stripped away Earth's ozone layer and caused a mass extinction. But space is vast, distances are enormous, we're safe. Magnetars don't last forever, thankfully. Their magnetic fields decay over time, releasing energy as they do. The field twists and reconnects, producing flares and bursts. Gradually, over perhaps 10,000 years, a magnetar calms down and becomes an ordinary neutron star. But during their brief, furious youth, they're among the most extreme objects we know of in the universe. And yet, even magnetars pale in comparison to what we're about to discuss. Because there are objects in the universe where gravity becomes so overwhelming that not even light can escape. Let's talk about black holes. A black hole is, in some ways, elegantly simple. It's a region of space-time where gravity is so strong that nothing, not matter, not light, not information, can escape. That's it. That's the core definition. But the implications cascade outward in ways that challenge everything we think we understand about physics and reality. When a massive star's core collapses into a neutron star, neutron degeneracy pressure eventually halts the collapse. Neutrons packed tightly together resist being compressed further through a quantum mechanical effect. But if the core is massive enough, if it contains more than about 2 to 3 solar masses, even neutron degeneracy pressure isn't sufficient. The collapse continues. Nothing can stop it. No known force in physics can provide the pressure needed to support that much mass in that small a space. The core falls inward, compressing further and further. It crosses a point of no return called the event horizon. The event horizon isn't a physical surface. There's nothing there you could touch. It's simply a boundary in space-time, a one-way membrane. Cross it in one direction, and you can never cross back. Once you're inside the event horizon, every possible future path you could take, every direction you could move, every choice you could make, leads deeper inward toward the center. Escape becomes not just difficult, but literally fundamentally impossible. The future itself points only one way, inward toward the singularity at the center. We don't know what happens at the singularity. Our theories break down there. General relativity, which describes gravity beautifully everywhere else, predicts that matter collapses into a point of infinite density. But most physicists suspect that prediction isn't quite right. At such extreme densities, at such small scales, quantum mechanics must become important. But we don't yet have a complete theory that combines quantum mechanics and general relativity. That's one of the great unsolved problems in physics. So the singularity remains a mystery hidden behind the event horizon. And perhaps that's for the best. The universe seems to obey what's called cosmic censorship. Singularities are always hidden inside black holes. We never see them exposed to the wider universe. It's as if nature is modest, keeping its most extreme secrets veiled. Black holes come in different sizes, different masses. The smallest are stellar mass black holes, formed from the core collapse of massive stars. These typically have masses from about 5 to a few dozen times the mass of the Sun. Their event horizons are small, just a few to maybe 100 kilometers across. We think there are tens of millions of these stellar mass black holes in our galaxy alone. Most of them are completely invisible, drifting silently through space. We only detect them when they happen to be in a binary system with a normal star. Gas from the companion star spirals into the black hole, forming an accretion disk that heats up and glows brightly in X-rays. Then we can see them. Then there are intermediate mass black holes. These would have masses from about 100 to 100,000 times the Sun. We think they exist, but we haven't confirmed many candidates. They might form from the direct collapse of very massive stars in the early universe, or from the merger of many smaller black holes in dense star clusters. The evidence is still being gathered. And then there are the giant, supermassive black holes. At the center of nearly every large galaxy, including our own Milky Way, there sits a supermassive black hole. These monsters have masses from millions to billions of times the mass of the Sun. Our galaxy's central black hole is called Sagittarius A*, or SGR-A* for short, pronounced Sagittarius A*. It has a mass of about 4 million suns. Its event horizon, the point of no return, would fit comfortably inside the orbit of Mercury. That sounds enormous, but it's actually one of the smaller supermassive black holes. The black hole at the center of the galaxy Messier 87, about 55 million light-years away, has a mass of about 6.5 billion suns. It's the black hole we famously imaged in 2019 through the Event Horizon Telescope collaboration. That image, showing a ring of light surrounding a dark circle, is one of the most remarkable photographs ever taken. The light in the ring is coming from gas swirling around the black hole at nearly the speed of light, heated to billions of degrees. The dark circle in the middle is the black hole's shadow, the region where gravity is so strong that light can't escape, or where light is bent so severely it can't reach us. The shadow is larger than the event horizon itself because the black hole's gravity bends light rays from behind it, making it appear bigger. That image confirmed decades of theoretical predictions. It showed us directly that event horizons exist, that black holes are real. But black holes aren't just dark, quiet objects sitting in space. They can be violent, extraordinarily violent. When matter falls toward a black hole, it doesn't just drop straight in like water down a drain. Conservation of angular momentum prevents that. The matter has to spiral inward, forming what we call an accretion disk. And an accretion disk around a black hole is anything but calm. Matter in the disk spirals inward slowly at first, but it accelerates as it gets closer to the black hole. Friction between particles, between different parts of the disk, moving at different speeds, heats the gas. For stellar mass black holes, the accretion disk might be only a few dozen to a few hundred kilometers across, but it can shine as brightly as millions of suns, outshining entire star clusters. For supermassive black holes, the disk can stretch for billions of kilometers, and the energy output can exceed the light from hundreds of billions of stars. 1 trillion suns worth of energy, pouring out from a region smaller than our solar system. This is what powers quasars. The name quasar comes from quasi-stellar radio source. When they were first discovered in the 1960s, they looked like stars in photographs but emitted unusual radio signals and had strange spectra. It took years to realize what they were: supermassive black holes in the early universe, surrounded by enormous, brilliant accretion disks, feeding voraciously on gas and stars. The most luminous quasars shine with the light of 100 trillion suns. A single object, brighter than 1,000 galaxies. And all that energy, all that light, comes from gravitational potential energy. From matter falling into a black hole, converting a fraction of its mass into energy with extraordinary efficiency, more efficient than nuclear fusion, more efficient than anything except matter-antimatter annihilation. Black holes, in a sense, are the most efficient engines in the universe, but the accretion disk is only part of the story. Many black holes, especially supermassive ones, can launch jets. These are narrow beams of matter and energy, accelerated to nearly the speed of light, and shot outward from the poles of the black hole. The jets can extend for millions of light years, far beyond the galaxy that hosts the black hole. They plow through intergalactic space, carrying enormous amounts of energy and momentum. When the jets collide with gas clouds outside the galaxy, they create enormous lobes of radio emission, sometimes larger than galaxy clusters. The mechanism that creates these jets isn't completely understood yet. It involves the black hole's magnetic field, which gets amplified and twisted by the swirling accretion disk. Somehow, this magnetic field channels energy and particles into two narrow beams that escape along the rotation axis of the black hole. The details are complex, involving magnetohydrodynamics, plasma physics, general relativity. We're still working it all out, but the effects are clear. Jets regulate the growth of galaxies. When a supermassive black hole is feeding actively, when it's surrounded by a bright accretion disk and launching powerful jets, it can blow gas out of the galaxy entirely. This gas would otherwise cool and form new stars, but the jets heat it up and push it away. Star formation slows or stops. The galaxy evolves differently than it would have without the black hole. Conversely, when the black hole isn't feeding, when it's quiet, gas can cool and collapse, forming new stars, some of which will eventually feed the black hole, spinning the cycle up again. Galaxies and their central black holes grow together in a delicate, violent dance that's been going on for billions of years. There's a remarkable correlation between the mass of a galaxy's central black hole and the properties of the galaxy's central bulge. Bigger bulges have bigger black holes in a very precise relationship. This suggests that the black hole and the galaxy evolved together, each influencing the other's growth. It's one of the most fascinating areas of modern astrophysics. And sometimes matter doesn't just trickle into a black hole gradually through an accretion disk. Sometimes an entire star gets too close. Every black hole has what's called a tidal radius. It's the distance at which the tidal forces from the black hole become strong, enough to tear apart an object held together by its own gravity. For a supermassive black hole, this tidal radius can be outside the event horizon. That means a star can be torn apart before it even crosses the point of no return. Here's how it happens. A star wanders too close to a supermassive black hole. Maybe it was on an eccentric orbit. Maybe it was perturbed by a gravitational interaction with another star. As it approaches, the gravitational force on the near side of the star, the side closest to the black hole, becomes much stronger than the force on the far side. This difference is the tidal force. It's the same force that causes ocean tides on Earth, caused by the difference in the moon's gravity from one side of Earth to the other. But near a black hole, the tidal forces are immense. The star begins to stretch. It elongates in the direction toward the black hole. If the star crosses the tidal radius, the stretching becomes catastrophic. The star is torn apart, shredded into a long stream of gas, like spaghetti. Astronomers actually call this process spaghettification, though the more formal term is tidal disruption. About half of the star's material, the half that was moving in the right direction, escapes the black hole entirely and is flung out into space. The other half, lacking enough energy to escape, spirals inward and forms a temporary accretion disk around the black hole. For weeks or months, the black hole suddenly has a feast. The accretion disk flares brilliantly in ultraviolet and X-ray light. From Earth, from millions or billions of light years away, we see a distant galaxy suddenly brighten dramatically, then slowly fade back to its normal state over the course of months. We call these events tidal disruption events, or TDEs. We've observed dozens of them now. Each one is slightly different depending on the type of star that was disrupted, the mass and spin of the black hole, the angle of approach. But they all tell fundamentally the same story. A star that wandered too close and paid the ultimate price. It's a reminder that black holes aren't just abstract theoretical objects. They're real, physical things that have measurable effects on their surroundings. And they're surprisingly common. In our galaxy alone, there are probably tens of millions of stellar mass black holes, most of them invisible, drifting quietly through space. Only when they accrete matter, or disrupt a passing gas cloud, or merge with another compact object, do they light up and reveal themselves. The universe is full of hidden violence, waiting in the dark. But there are events even more powerful than anything we've discussed so far. Let's talk about gamma-ray bursts. For a few seconds, or sometimes a few minutes, a gamma-ray burst is the brightest electromagnetic phenomenon in the universe. Not the brightest thing in a galaxy. Not the brightest thing in a galaxy cluster. The brightest thing in the entire observable universe. If you could see gamma rays, if your eyes were sensitive to that part of the spectrum, and a gamma ray burst went off in a distant galaxy, it would briefly outshine everything else in the sky combined. Every star, every galaxy, every quasar, all of it dimmed to insignificance by this one brief flash. The energy release is almost beyond comprehension. These events are so powerful, so energetic, that for a long time after their discovery, we couldn't figure out what could possibly produce them. Gamma-ray bursts were discovered by accident in the late 1960s by the Vela satellites, which were built by the United States to detect nuclear weapons tests in space. The satellites were equipped with gamma-ray detectors, and they started picking up brief flashes of gamma rays coming from random directions in the sky. At first, the military thought maybe the Soviet Union was testing nuclear weapons in space in violation of treaties. But the signals didn't match nuclear explosions, and they were coming from all over the sky, not from Earth orbit. Eventually, the data was declassified and published in 1973. Astronomers were baffled. What were these things? For decades, the mystery deepened. Were they from nearby stars? From distant galaxies? Were they happening in our galaxy? We couldn't tell because we couldn't pinpoint their locations precisely enough. The breakthrough came in the 1990s with the Compton Gamma Ray Observatory and later the Beppo-SAX satellite, which could localize gamma ray bursts precisely enough that optical telescopes could look for afterglows. And they found them, faint, fading points of light associated with distant galaxies, billions of light years away. That changed everything. If gamma-ray bursts were billions of light years away and still visible from Earth, they had to be extraordinarily powerful. More powerful than supernova. More powerful than anything we'd ever seen. We now know there are two main types of gamma-ray bursts, distinguished by their duration. Short bursts, lasting less than about 2 seconds, are thought to come from the collision of two neutron stars, or a neutron star and a black hole. Long bursts, lasting more than 2 seconds, and sometimes up to several minutes, come from the core collapse of extremely massive, rapidly rotating stars. Essentially, they're hypernovae seen from a special angle. In both cases, the mechanism involves the formation of a black hole and the launch of relativistic jets, narrow beams of matter and radiation moving at 99.99% or more of the speed of light. When one of these jets happens to point toward Earth, we see a gamma-ray burst. The energy is staggering. In a few seconds, a typical gamma-ray burst releases as much energy as our Sun will produce in its entire 10 billion year lifetime. The most powerful gamma-ray burst ever detected, GRB 080916C, released energy equivalent to about 5,000 supernova, all exploding simultaneously, all from one object, one dying star or one collision. If a gamma-ray burst went off within a few thousand light years of Earth and the jet pointed directly at us, the effects would be catastrophic. The gamma rays would hit our atmosphere and create a shower of secondary particles. The ozone layer would be partially destroyed. Ultraviolet radiation from the sun would increase. Ecosystems would be severely damaged. Mass extinction could result. Some scientists have speculated that a gamma ray burst might have been responsible for the Ordovician extinction event about 450 million years ago, one of the 5 major mass extinctions in Earth's history. But the odds are very much in our favor. Gamma-ray bursts are rare. In a galaxy like ours, we expect one every few 100,000 to a few million years. And the jets are narrow, covering only a tiny fraction of the sky. The chances of one happening nearby and pointing at us are extremely low. Space is vast. We're small. The universe is mostly empty. We're safe. But gamma-ray bursts do affect the universe as a whole. They enrich the cosmos with heavy elements created in the explosion and scattered into space. They sweep up surrounding gas, compressing it, sometimes triggering new waves of star formation. They're one of the ways the universe recycles matter, breaking down old stars and scattering their material for future generations. We're still learning about gamma-ray bursts. Every time we detect one, we learn something new about the physics of extreme events. In August 2017, something remarkable happened. The LIGO and Virgo gravitational wave detectors picked up a signal from 2 merging neutron stars. About 2 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same direction. It was the first time we'd ever detected the same event in both gravitational waves and light, a multi-messenger observation of a cosmic cataclysm. Within minutes, telescopes around the world swung toward the source. They caught the optical and infrared afterglow of the explosion, what's called a kilonova, a burst of light powered by radioactive decay of heavy elements created in the merger. Spectra of the kilonova showed clear signatures of gold, platinum, and other heavy elements. It was direct confirmation that neutron star mergers are a major source of these elements in the universe. Every gold ring, every piece of platinum jewelry, every silver coin contains atoms that were likely forged in one of these violent collisions, somewhere in the cosmos, billions of years ago. This multi-messenger event opened a new chapter in astronomy. Now we can observe the universe not just with light, but with gravitational waves, neutrinos, and cosmic rays all together. It's like going from seeing the world in black and white to seeing it in full color. Different messengers tell us different things, and together they create a much richer, more complete picture. For most of cosmic history, we could only imagine what happens when 2 black holes collide. We could write the equations. We could run computer simulations, solving Einstein's field equations numerically, but we couldn't observe it directly. That changed on September 14, 2015. Both LIGO detectors, one in Louisiana and one in Washington State, picked up a signal, a gravitational wave passing through Earth. The waveform lasted less than a second, starting at low frequency and sweeping upward in a characteristic chirp pattern. Encoded in that chirp was a story. 2 black holes, each about 30 times the mass of the Sun, had been orbiting each other for perhaps millions or billions of years. They formed from 2 massive stars in a binary system, stars that lived and died close together. As they orbited, they slowly radiated energy away in the form of gravitational waves. This caused them to spiral closer together gradually over immense stretches of time. But as they got closer, they moved faster. And as they moved faster, they radiated more energy. The spiral accelerated. In the final moments before merger, they were orbiting each other hundreds of times per second, moving at about half the speed of light. then they collided. For about a fifth of a second, the two black holes merged into one, ring-down oscillations rippling through the newly formed event horizon. And during that brief collision, the system released more power and gravitational waves than all the stars in the observable universe combined were releasing in light. More power than 100 billion trillion suns, all from two black holes merging silently 1.3 billion light-years away. The gravitational wave stretched and squeezed space as it passed through Earth. The LIGO detectors measured the effect. The two 4-kilometer-long arms of each detector changed length by about 1/10,000th the width of a proton, a distance far smaller than an atom measured across kilometers. It's one of the most sensitive measurements ever made, and it opened a new window on the universe. Since that first detection, we've observed dozens more black hole mergers. Each one teaches us something new. Some of the black holes are heavier than we thought possible from stellar evolution, suggesting there are formation mechanisms we don't fully understand. Some mergers involve black holes with very different masses, which tells us about how they formed and where they came from. Some have unusual spins tilted relative to the orbital plane, hinting at complex formation histories. We're learning how common black holes are, how they form, how they evolve, and we're testing general relativity in the strongest gravitational fields that exist. So far, Einstein's theory has passed every test with flying colors. But the universe keeps surprising us. In 2017, as we mentioned, we detected the merger of two neutron stars. This was different from black hole mergers in a crucial way. Black holes, when they merge, produce only gravitational waves. They have no surface. No matter outside the event horizon, there's nothing to shine, nothing to emit light. The collision is completely dark, visible only through the gravitational waves it produces. But neutron stars have matter. They have surfaces, crusts, magnetic fields. When they collide, they produce gravitational waves. Yes, but they also produce light. The collision creates a kilonova, a luminous transient event powered by radioactive decay. When the neutron stars merge, they create conditions of extreme temperature and density. Neutron-rich material is ejected into space at about 10 to 20% the speed of light. This material undergoes rapid neutron capture, the R process we mentioned earlier, synthesizing heavy elements all the way up to uranium and beyond. These newly created elements are radioactive. They decay, releasing energy, which heats the expanding debris and makes it glow. The kilonova brightens over hours, peaks in about a day, then fades over weeks. The color changes too, from blue to red, as the expanding material cools and becomes more opaque. For that August 2017 event, designated GW170817, astronomers observed the gravitational waves, the gamma-ray burst, the kilonova in optical and infrared light, and X-ray emission that appeared days later. It was the most thoroughly observed cosmic event in history, and it confirmed something we'd suspected for decades. Neutron star mergers are where most of the heavy elements in the universe come from. Gold, platinum, uranium, thorium, the elements that can't be made in ordinary supernova, the elements heavier than iron that require extreme neutron fluxes to form. They're forged in the incredible heat and neutron density of colliding neutron stars. then scattered into space to eventually become part of new solar systems, new planets, new worlds. The gold in any jewelry you might have, the uranium in nuclear reactors, the platinum in catalytic converters, all of it likely came from neutron star mergers that happened long ago in galaxies throughout the universe. It's a beautiful connection. Our planet, our bodies, our technology, all tied to the most violent collisions in the cosmos. Let's step back now and think about where all of this matter came from in the first place. In the beginning, just after the Big Bang, the universe was almost entirely hydrogen and helium, with just a trace of lithium. The lightest elements formed in the first few minutes of cosmic history. That's all there was. No carbon, no oxygen, no iron, no silicon, nothing heavier than lithium. Everything else had to be made later inside stars. Stars are the forges of the cosmos. In their cores, nuclear fusion builds heavier elements step by step. Hydrogen fuses into helium, releasing energy that makes the star shine. In more massive stars, when the hydrogen runs out, helium fuses into carbon and oxygen. The process continues up the periodic table: neon, magnesium, silicon, sulfur, all the way up to iron. But fusion stops at iron, as we discussed earlier. To make anything heavier, you need a different process. You need violence. In a supernova, conditions become extreme enough that neutrons can be rapidly captured by atomic nuclei, faster than the nuclei can decay. This rapid neutron capture, the R process, builds up heavier and heavier elements: zinc, germanium, silver, gold, platinum, uranium. About half of the elements heavier than iron are made this way in core collapse supernova. The other half, we now know, comes primarily from neutron star mergers. Every violent event we've talked about plays a role in this cosmic alchemy. Core collapse supernova scatter carbon, oxygen, neon, magnesium, silicon, sulfur, iron, and some heavier elements into space. Hypernovae and pair instability supernova create unusual elemental abundances, seeding the early universe with the first metals. Type Ia supernova, the white dwarf explosions, produce large amounts of iron and nickel. Neutron star mergers forge gold, platinum, rare earth elements, uranium. Even the jets from supermassive black holes play a role, pushing material around, mixing elements from different sources, triggering new rounds of star formation in some regions while suppressing it in others. All of this material, ejected and scattered, eventually collects into new clouds of gas and dust. Gravity pulls the clouds together. They fragment, collapse, heat up. New stars form. And around those stars, from the leftover material in the disk, planets form. Our own solar system formed about 4.6 billion years ago, from a cloud enriched by countless generations of stars that lived and died before the sun was born. The cloud collapsed, the sun ignited, and planets coalesced from the disk of dust and gas around it. The oxygen you're breathing right now was made in a massive star that exploded as a supernova billions of years ago, probably thousands of light years away from where our sun would eventually form. The calcium in your bones, the iron in your blood, the carbon in every cell of your body, all of it was forged in stellar furnaces and scattered by explosions. We are quite literally made of stardust. Not metaphorically, literally. Every atom in your body, except for hydrogen, was created inside a star or in the collision of two neutron stars. We are the universe's way of knowing itself, and the violence that created us, the supernova and collisions and explosions, is still happening out there, constantly, enriching the cosmos. Every second, somewhere in the observable universe, a star is exploding. Every few minutes, a neutron star is being born. Every hour or so, a tidal disruption event is shredding a star. Every few days, a gamma-ray burst is lighting up a distant galaxy. The universe is extraordinarily active, continuously creating and destroying, forging and scattering, building and recycling. And all of it happens in silence. This violence doesn't just create, though, it regulates. Supernova explosions inject energy into their surroundings. The shock waves push gas around, heating it, compressing it in some places, dispersing it in others. In regions where many stars are forming, where many massive stars will soon explode, the combined effect of multiple supernova can blow gas out of the galaxy entirely. This slows down star formation. It prevents the galaxy from using up all its gas too quickly. Without this feedback, without the regulation provided by stellar explosions, galaxies would evolve very differently. They'd be denser, hotter, perhaps less hospitable to stable planetary systems. Black hole jets provide even more dramatic feedback. In galaxy clusters, the largest gravitationally bound structures in the universe, there's hot gas filling the space between galaxies. This gas can cool and fall into the galaxies, where it would form new stars. But the supermassive black holes at the centers of the largest galaxies in these clusters launch powerful jets that plow through the surrounding gas, heating it, preventing it from cooling. Without this heating, the central galaxies would form stars at a much higher rate. They'd be very different objects. The jets regulate star formation on the scale of entire galaxy clusters. It's a beautiful feedback loop. Stars form, live, and die. Some explode as supernova, enriching the gas and regulating future star formation. Some leave behind black holes, which eventually grow and launch jets that regulate star formation on even larger scales. The universe is self-regulating, in a sense. Violence and creation in balance. And this has been going on for more than 13 billion years, since the first stars lit up the cosmos. Those first stars, formed from nearly pure hydrogen and helium, were probably very massive. Hundreds of times the sun's mass, perhaps. They lived briefly, a few million years at most, and exploded as hypernovae or pair instability supernova, enriching their surroundings with the first heavy elements. This allowed the next generation of stars to form with slightly more complex chemistry, and the generation after that had even more metals. Each cycle added more elements, more complexity, until eventually planets could form with solid surfaces and complex chemistry. Until eventually, billions of years later, on at least one planet orbiting an ordinary star in an ordinary galaxy, life emerged. And some of that life eventually developed the ability to wonder, to look up at the night sky and ask questions. Where do we come from? What are stars made of? How old is the universe? What happens when stars die? We've answered some of these questions. We've traced the elements in our bodies back to their origins in dying stars. We've measured the age of the universe. We've mapped the life cycles of stars. But every answer raises new questions. How do the most massive black holes form in the early universe? What exactly happens at the core of a neutron star? Are there exotic objects we haven't discovered yet? What new physics might we find in the most extreme environments? The universe keeps teaching us if we're willing to learn. If we're willing to build the instruments, do the observations, think carefully about what we see, and we are learning constantly. We've built telescopes that can see across the entire electromagnetic spectrum. Radio telescopes with dishes hundreds of meters across, or arrays of smaller dishes spread across continents, working together. Infrared telescopes that can see through dust clouds to where stars are being born. Optical telescopes with mirrors 10 meters across, using adaptive optics to correct for the blurring effects of Earth's atmosphere. Ultraviolet, X-ray, and gamma-ray telescopes in space, above the atmosphere that blocks these wavelengths. Each type of telescope shows us something different. The James Webb Space Telescope, launched in December 2021, looks deeper into the infrared than any previous telescope. It's seeing the first galaxies that formed after the Big Bang, studying the atmospheres of planets around other stars, watching stars being born in nearby nebulae. The Vera Rubin Observatory, expected to begin operations soon, will photograph the entire visible sky every few nights. It will catch transient events we would have missed before. Supernova, tidal disruption events, asteroids, anything that changes or moves. Future gravitational wave detectors, like the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will be far more sensitive than LIGO. They'll detect neutron star and black hole mergers across the entire observable universe, seeing mergers from when the universe was young. There's even a proposal for a space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna, which would be sensitive to lower frequency gravitational waves from supermassive black hole mergers. We're entering what many call a golden age of astronomy, where we can observe the universe in ways that were impossible just a few decades ago. And every discovery raises our sense of wonder. There's something deeply meditative about the silence of all this violence. Here on Earth, we associate violence with noise, explosions, thunder, roaring, breaking, crashing. Sound and violence seem inseparable in our everyday experience. But out there in the cosmos, the most powerful events imaginable unfold in complete silence. A star collapses and explodes, releasing more energy than we can really comprehend. Silent. Two black holes spiral together and merge, shaking space-time itself, releasing more power than all the stars in the universe. Silent. A magnetar's crust cracks, releasing a burst of energy that could devastate a planet from thousands of light years away. Silent. It's humbling. It reminds us that the universe doesn't perform for us. It doesn't need our perception to exist. It simply is following the laws of physics, doing what it does, whether we're watching or not. These events happened for billions of years before humans existed. They'll continue for trillions of years after we're gone. A supernova explodes in a distant galaxy. The light travels for millions of years through empty space. Eventually, if someone on Earth happens to point a telescope in that direction at the right time, they'll see it. A new point of light in the sky, brightening and then fading over weeks. But by the time they see it, the event is ancient history. The shock wave has long since passed. The remnant has cooled and dispersed. The neutron star or black hole left behind is going about its quiet business. We're always looking into the past. The nearest star to us, Proxima Centauri A, is about 4.2 light years away. When we see it, we're seeing it as it was 4.2 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. We see it as it was 2.5 million years ago, when our ancestors were just beginning to make stone tools. The most distant galaxies we can see are over 13 billion light years away. We see them as they were when the universe was less than 1 billion years old, when the first stars were just starting to form. And in all that time, across all that space, the universe has been active. Stars forming and dying. Black holes growing, galaxies colliding and merging. Elements being forged and scattered, planets forming. Maybe, probably, life emerging in countless places, all of it in silence. It's beautiful, in a way. The universe is so vast, so full of activity and energy and change, and yet it doesn't announce itself. It doesn't shout or proclaim. It simply glows, radiates, creates ripples in space-time, and we've learned to listen. We've built instruments sensitive enough to detect the faintest glimmers of light from the edge of the observable universe. From galaxies so distant, their light has been traveling for most of cosmic history. We've built detectors that can feel space-time stretch by less than the width of a proton, catching gravitational waves from events billions of light years away. We've built neutrino observatories that can catch a handful of ghostly particles from a supernova explosion. And with these tools, we've learned to hear what the universe is saying. Not with sound, with light, with particles, with gravitational waves. We've learned to translate the universe's language into something we can understand. And the story it tells is extraordinary. We live on a small planet, third from an ordinary star, in the outer suburbs of a spiral galaxy. That's one of hundreds of billions in the observable universe. By any objective measure, we're tiny, insignificant, perhaps. And yet, we're made of atoms forged in the hearts of stars, scattered by supernova, swept up in the cloud that formed our solar system, assembled into molecules, into cells, into living beings capable of wonder. We are connected to the universe in the most fundamental way possible. We're not separate from it. We're not observers looking at something distant and foreign. We are part of it, made of it, expressions of it. The iron in your blood, carrying oxygen to your cells, was made in the core of a massive star that exploded as a supernova billions of years ago. The calcium in your bones was forged in stellar fusion. The gold in any jewelry you might have was created in the collision of two neutron stars, an event so violent it briefly outshone a galaxy. Every breath you take contains oxygen atoms that were made inside a dying star. We are quite literally the universe looking at itself, matter that has become conscious, asking questions about where it came from. It's one of the most profound realizations you can have. The violence we've been exploring tonight, as extreme as it is part of what made us possible. Without supernova, there would be no heavy elements, no rocky planets, no chemistry complex enough for life. Without the regulation provided by black holes and stellar feedback, galaxies would have evolved differently. Star formation would have been chaotic. Stable, long-lived stars like our sun might be rare. The universe's violence is also its creativity, and we're here because of it. When you look up at the night sky at the stars scattered across the darkness, you're seeing the results of billions of years of cosmic violence and creation. Those stars are fusion reactors, converting hydrogen into helium and releasing energy. Some of them will eventually explode, scattering their material to form new stars, new planets. The darkness between the stars isn't empty. It's filled with gas and dust, the remnants of previous generations of stars. It's the raw material for future creation. And scattered throughout our galaxy are objects we can't see with our eyes. Neutron stars spinning hundreds of times per second. Black holes, some solitary, some feeding, some launching jets. White dwarfs slowly cooling. Supernova remnants expanding and fading. All of it part of the great cycle of stellar birth and death that's been going on since the first stars formed more than 13 billion years ago. And it will continue. Long after we're gone, stars will continue to form and die. Black holes will continue to grow and merge. Galaxies will continue to evolve. In about 4 billion years, our own galaxy, the Milky Way, will collide with the Andromeda Galaxy. The night sky will look dramatically different for any observers that might be around. The collision will trigger new bursts of star formation. Eventually, the two galaxies will merge into a single, larger elliptical galaxy, and the universe will continue expanding, carrying distant galaxies away from us. Eventually, trillions of years in the future, star formation will slow as galaxies use up their gas. The universe will grow darker, quieter. Black holes will grow larger, swallowing more matter. Eventually, through a process called Hawking radiation, even black holes will evaporate, releasing their mass back into space as particles and radiation over timescales, so long they're hard to even imagine. But that's far, far in the future, unimaginably far. For now, the universe is vibrant, active, creating and destroying in equal measure, and we're lucky enough to be here in this brief moment of cosmic time, able to observe it, study it, wonder at it. As you drift towards sleep, think about this. Right now, this very moment, somewhere in the universe, a star is exploding. Multiple stars, actually. The universe is so vast that several supernovae are probably happening every second across the observable universe. Right now, neutron stars are spinning silently, hundreds of times per second, their magnetic fields channeling radiation into beams that sweep across space. Right now, black holes are feeding, growing, launching jets that extend for millions of light years. Right now, two black holes or two neutron stars might be in the final moments before merger, spiraling together, about to collide and send ripples through space-time. Right now, gamma-ray bursts are going off in distant galaxies, outshining everything around them for brief, spectacular moments. All of it in silence, all of it governed by the same physical laws that govern everything on Earth. Gravity, electromagnetism, the strong and weak nuclear forces, quantum mechanics, general relativity, the same laws playing out in the most extreme environments imaginable. And we've figured out how to observe these events, how to detect them, measure them, understand them. Not perfectly, not completely. We still have so much to learn. But we're learning. We're building better instruments. We're developing better theories. We're asking better questions. And the universe keeps revealing its secrets, one discovery at a time. You don't need to remember all the details. You don't need to keep track of every number, every name, every process. Just hold on to the wonder. The universe is vast, ancient, and full of extraordinary things. Stars explode with unimaginable power. Black holes merge and shake reality itself. Neutron stars spin hundreds of times per second, their magnetic fields warping empty space. And all of it happens in silence. Not because there's anything wrong or missing, but simply because there's no air in space to carry sound waves. But we've learned to listen anyway. With telescopes, with detectors, with satellites and observatories scattered across Earth and in space, we've learned the universe's language. And it's telling us a beautiful story about how everything came to be, about where the elements came from, about how galaxies form and evolve, about the life cycles of stars, about how violence and creation are two sides of the same cosmic process, about how we, tiny and brief as we are part of something vast and ancient made of stardust, born from violence billions of years ago, connected to the universe in the most fundamental way. So rest easy now. The stars are still out there doing what they've always done. The universe continues its ancient dance of creation and destruction, building and recycling, forging elements and scattering them into space. Black holes grow, neutron stars spin, supernova explode, all in silence, all following the laws of physics with perfect precision. And tomorrow, when you wake, the universe will still be here, still active, still full of wonders we're only beginning to understand. There will be new discoveries waiting, new mysteries to explore, new questions to ask. But for now, let it all drift away. The violence is distant, the silence is complete, and you are here, safe, connected to it all through the atoms in your body, forged billions of years ago in the hearts of stars. Sleep well. The cosmos will keep watch. The stars will continue their slow journeys across the night sky. The gravitational waves will continue rippling through space-time. The universe will continue expanding, evolving, creating. And we'll be here tomorrow to wonder at it all again. Until then, rest. The universe's most violent things are silent. And so for now, can you be? Good night.